Welcome to another video explaining the universe using the particle model. Today's video is about the homopolar train and rolling battery. Made a previous video explaining the homopolar motor, and this is a continuation of that. In the previous video, I described a homopolar motor, and the train and the rolling battery have the same three parts. There's a armature, which normally is a copper wire, but can also be an aluminum foil, which is used in the rolling battery. Then there's a 1.5 volt battery, and finally usually one or two batteries. And in the train, they use two batteries, two magnets, excuse me. The battery is 1.5 volts, and the magnets are neodymium rare earth magnet, and they're the most powerful magnets in the world. They're made from neodymium, iron, and boron. They are dangerous. You can hurt yourself if you ever get some and play with it, so please be careful. So I'm going to show you a video of the train. And this is the same video I used last time for the motor. So let's take the time and look and get the standard explanation for the homopolar train.
In most homopolar motors, the batteries and magnets are held steady while the wire rotates around them. In the homopolar train, the wire in the form of a tightly wound coil is fixed and the battery and magnets move through it. How it works is that electricity from the battery flows through the magnets into the coil, down the coil, and to the back of the battery. This section of the coil, which is carrying the current, creates a magnetic field. These magnets are set up so that they're opposing each other. In other words, this is a south end, and this is a south end. This is a north end, this is a north end. And what happens is that when the battery's polarity is correct, this magnet is repelled by the field inside the coil, and this one is attracted to it. So it moves along by being pushed forward or repelled by the front magnets and attracted or pulled by the rear magnets.
Okay, so there we have the video, and let's move on to just to recap the standard explanation of the train. There is magnetic attraction and repulsion. He has a current, the plus side of the battery is here, current is going around and back around this way. The south pole of the magnets are out here at the ends, and the north pole is attached, connected to the battery. And he didn't mention the direction of the coil, and of course, does that even matter? Because it might be a question. So I looked at that. I found a different explanation, and it looked like they understood what they were doing. This is from Skull in the Stars website. And what they did was they take the battery that's symbolized here and the coil current there and change it to a virtual magnet so that you have south and north ends, which makes it easier to some people to understand that south and south repel and north and south attract. But then I wanted to check whether this connection between the plus battery and the south was correct, and I got this, and sure enough, here's plus and south. But if you take your right hand and you put it here with the current going up in the front, and you take your right hand, you'll see that the magnetic field goes towards the north. Okay, and so you do the same thing on this battery here with the coil going this way, and you see that the magnetic field goes up, but not to the south, it goes to the north. It seems like he has this reversed. Now, the explanation is that there is a pushing effect here by repulsion. Repulsion would push it, and then there is the attraction where it gets pulled. And one of the questions I had was, is that really attraction? Last time I showed a video where I showed myself how it doesn't matter which way you put the battery on the magnet, it clamps onto it because it connects to the other parts of the body of the battery, which has nothing to do with the charge, the plus or minus charge of the battery, and so on. So anyway, it turns out that the direction of the coil does matter. There are 4 ways to have the battery and the coil put together, but there's only 2 ways for the electric field to move. Okay, so I decided to really closely look at the way that coil was in the video, and I took the picture of this right here where there's a shadow, and because of this shadow right here, it appears that the coil, the physical coil, is going down in front, in and back, in and the bottom, up in the back. And of course, because of the flow of where the battery was connected on the left side, the flow of the current moves to the right, excuse me, not left. So that's the direction, and putting all that together, I have this particular explanation. The battery is to the here, as you can't tell from looking, but he said that in the video. The plus side is here. The south side is on the magnets are on the outside. The north connected to the battery. And the coil is wound. I extended this way out here so it's a little clearer. It's down in front, in at the bottom, up at the back. That's the direction of the coil, and it turns out for the standard model explanation, you've got G1s flowing this way. And so it's down in front, in and back, up, in at the bottom, up at the back. And when you do that, you use your left-hand rule. You have to do that with the particle model, left-hand ruled, and the magnetic field is going from left to right. And also the magnets, I've done this before, where the G1 particle flow inside a magnet flows from north to south, and here north to south. So here you end up repulsion at the end of the train, not at the beginning. It maybe has to do with that flip on the virtual battery or whatever was confusing the person who did the video. But you have repulsion here, which essentially is a push on the train. Now the coil doesn't move. The coil doesn't move. And you have a virtual wall, if you will, with the flow of the magnetic field of the battery and coil. You have the magnet coming here trying to push against that field, pushing yourself away. It's sort of like when you're leaning against a wall, you can push yourself away from the wall, making yourself go backwards. So that is the direction that it moves. Turns out if you go through all the scenarios, I didn't go through all of them, but as in the train, in the experiment, you can simplify the direction by saying the direction of the magnetic field is the direction that, because even if the repulsion is here and not here, then that magnetic field is pushing this magnet. Here the magnet is sort of pushing itself away from the magnetic field. Okay, rolling battery. Video explains that this is just like a railgun. And the diagram here shows the gravity, the F2, this is the G2 gravity, pushing the foil backwards to make this roll forward. It's a tricky thing because we're going to see variations of the rolling battery, but we're going to watch and explain the one that's rolling towards you. So here's the rolling battery.
The homopolar motor has to be the rolling battery version. Current passing through the aluminum foil creates the force that pushes the battery along. The principle is the same as rail guns, which are being developed for military application. If one magnet is larger than the other, the battery will travel in a circle. And that's about all there is to know about homopolar motors. A homopolar motor has to.
Okay, so you can see at the end it was rolling towards us. And this is as I said earlier, just before the video, when you listen to it, he says it's just like the railgun, which kind of an interesting, just kind of almost a cop-out. But here's the particle model explanation. And I'm starting here, and I said this earlier because what's happening is this blue X says that the force is pushing in on the aluminum foil, and that's this way, and the aluminum foil doesn't move, it's fixed on the table, so then the battery moves towards us. So if you look at the well, you got to look at the fact that the magnets are connected to the aluminum foil at one point at the bottom. Here we're looking at the end view bottom. This is top view. This is looking at bottom. And so I drew this line, this portion of the magnetic field, as if it were a conductor. And so and that's true here. So you have a current, the G1 flow goes around and is going this way. Using the left-hand rule, you'll see that the magnetic field of that's around that current flow, G1 flow, is in on the top, down in the back, or out in the bottom, up in the front. And I designated that with the X and the O, down in the top, up in the bottom, here down in the back, up in the front. So the X represents the direction of the magnetic field around the copper wire as the G1 flows this way. Now I have here, he didn't tell us which way the the magnets are. And so I put the north on the outside. I could have put them on the inside like the other one, but I didn't. And when you do that, you have G1 flow inside the magnet from north to south, and this one north to south, setting up a downward field here at the on the tinfoil. And so the green X represents the fact that the magnetic field's going down here and down here on both sides. And so this is where the explanation of how the F2 force is generated, because you got G2 particles coming at this in both directions. And here you have twice the number, assuming that each field was identical. You have double the number of G1s here because they're going in the same direction with minimal collisions. And here at the where's my cursor? Here at the on this side, They're also double, but there's a lot of collision because they're opposing each other. They're coming at each other. They hit, they scatter. So I saying that there's fewer here. So that sets up a net force this way on the aluminum foil, causing it to roll that way. Notice that buildup of G1s behind this, the fin foil here and the smaller one in front, extend the whole way. It's not just one spot like I've shown here. There's a large mass of G1 here, a small mass of G1 there. And you always have a net force of gravity from the small object to the large, just like from the moon to the Earth. There's forces the other way, but there's a net force in that direction. That's why the battery rolls that way. Okay, magnets that have the same direction, I have north on the outside and south on the inside, making these the same direction. As far as the magnetic field around this part of the aluminum foil, it's the same, down and back, up and front, but this magnetic field is down and this one's going up. So there you've got green going down on this side, you've got green going up on that side, and you get opposing forces. I haven't tried this yet. I did try it once. I wasn't successful with my little effort. I didn't spend a lot of time, but I'm wondering myself, could this spin if you did that? Probably not, but it would be an interesting thing to see happen. All right, the conclusion. With the magnets in the opposite direction, it moves in the direction of the coil's magnetic field. That's a simple rule. And the force that pushes it is the G2 force. They talk about their answer is magnetic repulsion and attraction. With the magnets in the same direction, the train does not move. Rolling battery. With the magnets in the opposite direction, the force pushes the tin foil, causing the battery to roll in the opposite direction. With the magnets in the same direction, it doesn't roll. You would expect it not to roll, but maybe it could spin. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time while I explain more of the universe using the particle model. Thank you for your attention.